Okay, for this video we'll be doing the 2014 paper. Okay, so make sure you have done it. So let's start with question 1. A car of mass 950 kg. So this is actually my mass M. Alright, so please annotate. It has a speed of 20 meter per second at time equals to 0. That means at the starting time, when time equals to 0, the speed is already 20. So I'll mark it out here in the graph. Okay, then they say it accelerates at a uniform rate. That means this is constant acceleration. Okay, what does it mean if it's in a speed time graph? In a speed time graph, the gradient represents acceleration. So if the gradient represents acceleration, right? Therefore, later, I'm supposed to draw a constant gradient graph for the starting part whereby it's accelerating. So they have uniform rate of 3 meter per second square. That means every second the speed increases by 3. For how long? For 6 seconds. The car then travels at a constant speed for 4 seconds. So these are things that you need to take note of, right? Finally, the car is brought to rest. That means the speed is 0 in a further 5 seconds by a constant braking force. So I will mark out the time, 6 seconds. It travels at a constant speed for 4 seconds. 6 plus 4 will give me 10. And then it decelerates. Okay, brought to rest in a further 5 seconds. Okay, so later on when I'm plotting, I'll make use of the time. Now complete figure 1.1 to show how the speed of the car varies with time t for the whole journey. So I need to calculate from 20, it actually accelerated for 6 seconds. That means this is my A, T, and this is actually my initial speed of U. So I'm going to use this formula, A equals to V minus U over T, to find out what is the speed after 6 seconds. So I put in the numbers. A is 3, V is unknown, U is 20 and not 0 because we started off with 20. The total time for this acceleration is 6. So doing my math, I get 18 equals to V minus 20. Therefore, V is 38, right? So I need to mark carefully where is 38. Each square represents 2 units. So it will look something like this. Okay, why do I use a straight line? Because it is a constant acceleration, right? It accelerates at a uniform rate. So constant acceleration, that means the gradient must be a straight line, must be a constant gradient. So then it travels at this constant speed of 38 meter per second for 4 seconds, right? Excuse me. Finally, the car is brought to rest in a further 5 seconds by a constant braking force. So if I have a constant braking force, and you know F net equals to MA, right? So if my braking force is constant, that means my deceleration or my negative acceleration is going to be a constant. So I will draw a straight line. So if you manage to draw a straight line for this section A, B, and C, right, at all the appropriate time, then you will get your 3 marks. So using a graph in figure 1.1 to determine the distance traveled between t equals to 0 and t equals to 6 seconds. This is important because some students, they think that, oh, because I draw the graph from 0 to 15, I'm going to calculate the total distance. But they are only asking for this distance here from 0 to 6 seconds. Now, why did I shade the area over there? Because area distance in a speed time graph is represented by the area under the graph. Okay, so these are the two things that you need to know for speed time graph. Okay, to summarize speed time, you need to know that firstly, gradient represents acceleration, and area under the graph represents distance travel. Okay, because the first question they already asked us to use this important concept. So of course the next question they will ask us to calculate the distance. So it's actually a trapezium. If you're not comfortable, you can break it up into a triangle. Okay, I'm going to use the trapezium method. I will sketch out this trapezium. Over here is 20. Here has a height of 38. and the total time duration is 6. So trapezium formula, the area is equals to half times the common base, which is 6, times the sum of the parallel heights. So in the end, I will get a value of 174 meters. Then lastly, they ask us to calculate the resultant braking force as it is brought to rest. Now this happens from t equals to 10 to t equals to 15. Okay, so there is a deceleration. And you take note that it is actually 3 marks. So the formula resultant force is F net equals to ma. Okay, if you have read the question, you were given m. But how about the acceleration? The acceleration actually is not given, but you can actually again use this gradient which represents acceleration. Okay, from time 10 to time 15, you can calculate the acceleration. Okay, so the acceleration, we have to make use of this formula, a equals to v minus u over t. The acceleration is what I want to know. The final velocity is actually 0. Okay, the initial velocity at time equals to 10 seconds is actually 38 meters per second. So you need to take note of this and not to use 20. So over this total time duration of 5 seconds, because it's from 10 seconds to the 15 seconds. So that will give me a value of minus 7.6 meter per second square. Now the braking force, F net equals to ma. So my mass of this car, let's look back, the mass is actually 950. So for calculation questions, it's very important to annotate actually all these values. So I put in my 950 multiplied by my 7.6. Okay, why not negative? Because it is actually the braking force, right? They are just asking us to calculate the braking force. So braking force will suggest that the speed decreases. So I'm dropping the negative sign. In the end, I will get 7220 newtons. Okay, and so for this will be 2 marks. This one, I guess, will be 1 mark, right? Let's go to question 2. In a whitewater canoe course, water flows from a lake. Take note of where's the lake. Through the course and into a reservoir. So this is the lake and this is the reservoir. Water is pumped back up into the lake. That means there is actually a downward flow. The volume of water pumped per minute from the reservoir to the lake is 780 meter cube. So this is volume per minute, right? It says per minute. So it's not just your volume, it is volume per minute. That means every minute, the water that's pumped from reservoir to back to the lake is 780 meter cube. The water is raised through a vertical height of 5.50. Alright, so this is height. So I'll put it as H. Water has a density of 1000 kg per meter cube. So density is 1000 kg per meter cube. Calculate the mass. Now mass, we give it a letter of m. So what are the formulas that has mass, density and volume in it? So density equals to mass per volume. And because they're asking us for the mass of water pumped per minute, and the volume pump is actually 780 meter cube per minute, so we don't really need to care about the per minute now. So density is 1000, the mass is unknown, the volume is 780. Therefore, that will give me the mass of 780,123 kg. Okay. Next, the height of water pumped per minute into the lake. The weight. They give us G. So W equals to mg. And just take note that everything is in SI unit. Yes, my mass is in kg. So it's going to be 780,123 multiplied by 10. Therefore, it is equals to 780,000 newtons. Okay, so if you key into your calculator and they give us like a standard form or even times 10 to the power of a certain value, you can also write it down. So just be careful when you're transferring, make sure that all the zeros are correct. Okay, I have had students who write this and then after that in the end their answer lack of 1 0. Okay, so just be careful. Now calculate the total work done per minute. So there's still total work done per minute by all 5 pumps. Okay. So each pump is all the pumps are actually working together using 5 large pumps, right? So that is the volume of water that is pumped up. So the work done per minute by all 5 pumps, remember what's the formula for work done? Equals to force times distance moved. Okay. The force is actually 780.1234 multiplied by the total distance of 5.5. Okay, so I'll get a value of around 4.29 times 10 to the power of 7 joules. Okay, but what if somebody wants to calculate using GPE? Okay, so GPE, as you know, is mgh. Yes, if I use my mg is actually equals to the weight. Do you see that? And the height will then still be 5.5. So it will give the same value of 4.29 times 10 to the power of 7. Okay, so now they want us to calculate the average output power of each pump. So this is something to be taken note of. Okay, so over here they are asking for the total work done by all 5 pumps. But now they want the average output power of each pump. So later we need to make it that is by per pump. So what's the total work done? Total work done from part C is equal to 4.29 times 10 to the power of 7. Okay, so this is per minute. Per minute. So 1 minute we actually have 60 seconds. Alright. So what is the power for the whole system? Power is rate of energy transferred per unit time. My energy required is 4.9 times 10 to the power of 7. The time is 60. Yes. So I will have a certain value. But this, after that, I need to divide by 5. It is equal to 715,000 watts. Okay. So by the whole system of the 5 pumps, the power, output power is 715,000 watts. But because they're asking for each pump, so I need to take 715 divided by 5. I will get a value of 1.43 times 10 to the power of 5 watts. So this question is actually not very difficult, but if you didn't read carefully, then you will not get the same answer. Alright. So let's move on to question 3. When I look at this, I see this word, I know we are dealing with moments. Right? Every time there's pivot, it's going to be moments. Okay, so let's read on. The newspapers are soaked in water. Soaked paper is packed into the container. When a force F is applied at the end of the handle, this is my force F, the plate squeezes the water out of the paper and leaves a block. The area of the plate in contact with the paper is 0.025 meters square. Where is this? Over here. So this plate area has a area of 0.025 meters square. Perpendicular distance from the pivot, which is here, to the rod holding the plate. Where's the rod holding the plate? This is the rod. Holding the plate is 10 cm, so I have it here. So that is the perpendicular distance. A force F is applied normal to the handle, which is here. Right, normal to this handle at a distance of 30 cm from the pivot. So actually they are helping us by giving us the perpendicular distance of the forces. Now we have a pressure of 7,200 Newton per meter square. So this is actually 7,200 Pascal, right? Because if it's expressed in Newton per meter square, then it can be Pascal. It is needed to squeeze the water out. So calculate the force that's exerted by the rod. To cause a pressure of 7,200 Newton per meter square. So pressure's formula is force over area. Pressure is given, force is unknown, we are asked to find, and area is given as 0.025 meter square. So let us put in the value 7,200 multiplied by 0.25 equals to F. Therefore, my force is 180 newtons. Okay, So the force applied at the end of the handle to exert a pressure of this, right? So continuing from part A, what is this force required? Okay, so now there are actually two forces. This force F is unknown. There's this force of 180 newtons. Okay, so this may sound a little bit complicated because this is the 180 newton that's pressed downwards to compress the newspaper, right? But if you're talking about this handle, what are the forces acting on the handle? I'm going to draw it over here. So this is the pivot. Okay, I apply a force here. So this is a force exerted on this handle. Okay, now if the 180 newton is pressed down on the newspaper is actually going to press up with a 180 newton force back on the handle. I say again, the handle presses this plate down with a force of 180 newton on the newspaper. By Newton's third law, the newspaper is going to exert back 180 newtons. Okay, why do I have to say this? Because if I still draw my 180 newton downwards, then later on when we calculate moments, it will look very strange because both of these moments is going to be anti-clockwise. So there's no clockwise moment, then you'll be thinking sum of clockwise moment is 0, sum of anti-clockwise, there's a value. Then how can it be equal? So that's why you need to understand we are calculating the force or the moment exerted on the handle. Okay, so on the handle, put yourself in the shoe of the handle. You're pushing something down. You're pushing the newspaper down. The newspaper is pushing you up. So if you are the handle, the force of 180 newton is upwards on you. Then we have our perpendicular distance because this is a pivot. So pivot first step. Second step, there are two forces, F and 180 newtons. Then perpendicular distance is given to you. This is actually 10 cm. This is actually 30 cm. So 180 newton will have a force, will have a perpendicular of 10 cm to the pivot. The force F will have 30 cm perpendicular distance. So now we multiply them. The moment will be 30 F Newton cm. Okay, why don't I change it to meters? Because both sides are using cm. So this will be 1800 Newton cm. Okay, and this is going to be a clockwise moment. Step 5, you determine what's the direction of the moment. For this, it will be an anti-clockwise moment. Then you apply your principle of moment, whereby sum of clockwise equals to sum of anti-clockwise. So equals to 1800. Therefore, my force will be 60 newtons. Okay. So some of you actually don't run through the 6 steps. You all just do it by like that, and you get 60 newton. That's fine as well, right? So question 4 is not tested because it's not in our syllabus anymore because of this critical angle. Okay, but one word to take note is that you must always draw normal if it's not drawn for you. A lot of students make mistake by not drawing normal, but even if some students draw normal, this angle of 48 degrees, if you look at this, we use this for example, this angle of 48 degrees, it is actually not the angle of incidence because we always use the normal as the reference. So the angle of incidence on this face of AB is actually 42 degrees. Take note of that. Okay, so we skip this. Now question 5, a string on a guitar is plugged. It shows the variation with time of the pressure of the air near the guitar string. So this is time. So later on, I'm only able to get things like period. I cannot get wavelength. So this is a slight variation from our DD and DT graph. So just to recap, DD graph you can actually get. What is DD graph? It's actually displacement, which is our y-axis, versus distance, which is our x-axis. So from the y-axis, we can actually get things like amplitude. Okay, from the x-axis, which is distance, we can get things like wavelength. So this is important. You need to identify whether is it dd or dt graph. For dt, it is same thing, displacement in a y-axis. Your x-axis is now time. Okay, so displacement, y-axis, you can get amplitude. Time, x-axis, we can get period. What is period? Period is capital letter T. Period is a special time. It is a time taken period is the time taken to complete one wave. So if you have period, then you can calculate frequency, because T equals to 1f, 1 over frequency, or frequency equals to 1 over T. Okay, so these are the two graphs associated with wave. One is dd, displacement distance. The other one is dt, displacement time. However, now it's air pressure versus time. That means for the time, I can only get period. I cannot get anything like wavelength. If I have period, then I can later on find my frequency. Okay. The air pressure when there's no air is P air, which is here, right? The string is plugged again to produce a louder note with the same pitch. Same pitch means same frequency. That means no change in frequency. That means no change in period. Same period. That means the time taken to complete one single wave is the same. So later on I will end my graph here. Okay, my midpoint will be here. But because it's plugged again to produce a louder note. Louder note means larger amplitude. So I need to draw my graph with a higher amplitude. Okay, so I can draw it as long as my amplitude is higher than this, right? This is when it is first plugged. Now I need to draw something that's louder. I need to make sure that the air pressure is higher, because the air pressure is, when it's louder, is higher. Okay, so as long as I have anything like this, or even if I draw it somewhere here, but please make sure that the top part is equal to the bottom part. Okay, so something like this. Now the string is tightened and plugged again to produce a note of higher pitch. Did they say anything about loudness? No. So they just say higher pitch. Now higher pitch means higher frequency, but it will be a lower period. That means the period will decrease. Okay, because of this formula, F equals to 1 over T. So if my frequency increase, my period must decrease. Okay, must decrease. So how the graph will be different as a result of playing this new note. Okay, so the answer is a note of higher pitch, right? Because we start out with higher pitch, will have a higher frequency. This means that more complete wave will be seen, displayed on the screen in the same period of time. Okay, that means initially, if I have something like that, this is my original. Okay, and now if I plug it with a higher frequency, I will get more waves. Okay, because they wanted us to describe how the graph will be different. So we have to give reference to the graph. We cannot just stop at, oh, higher pitch, higher frequency, lower period, full stop. No, we must say there will be more complete waves displayed on the screen, which is the graph, in the same period of time. Okay, so if you didn't say how the graph will appear different, you just give this theory, you will not get that 1 mark. Okay. Okay, question 7. I think this is electrostatic or electricity. A large thundercloud becomes charged with a negative charge at its base, so seen over here. As shown in figure 6.1, a lightning flash occurs as a thundercloud loses some of its charge to the ground. One lightning flash delivers an average current So this is actually my I for a time of 0.00011 seconds. So this is time. So current I and time is given. Calculate the quantity of charge. So charge is actually Q, not C. So the formula is Q equals to IT. Okay, so this is easy 2 marks. 11000 multiplied by 0.00011. Please use your calculator, and the answer will be 1.21 coulombs. Okay, next. Tall buildings are fitted with thick strips of copper called lightning conductors as shown in figure 6.2. So this is actually my lightning conductor. The copper contains negatively charged particles, which are actually electrons. Right, remember only electrons are free to move within the copper. Okay, so the lightning conductor is attached to a large metal plate in the ground. So there's this large metal plate. Describe and explain what happens to the negatively charged particles in the copper when the thundercloud passes overhead. So remember, the thunderclouds was having negative, and only the negatively charged particles in the copper are allowed to move. So later on, I'm going to use this like charges repel. Okay, so let's look at the answer. When the thundercloud passes overhead, the negatively charged cloud repels the negative charges in the copper. So make sure you give ownership to the charges. The negative charges in the copper is being repelled by the negatively charged cloud, because like charges repel. This is the concept, right? So the negative charges in the copper will then move downwards, because over here they are repelled, the electrons are repelled downwards to the metal plate, resulting in an induced positive charge. Remember, positive charges cannot move. In chemistry, the positive charges, which are the protons, they are in the nucleus. You can't just take them out. It's only the electrons that are free to move, meaning I can either add in or take it out. So the electrons, if they are lesser, that means at the tip here, the number of protons will be greater than the number of electrons, right? So therefore, it will result in an induced positive charge at the top of the copper strip at the top of the building. Okay, so this is important. You need to mention the negatively charged particles in the copper, because they are the one that has moved. Okay. Okay, next question. Circuit contains a battery, 3 identical ammeters, A1, A2, and A3, and 2 resistors of resistance 4000, 2000. Okay, the reading on ammeter A1 is 2.0, so it's good to draw it here, 2.0 milliampere. And this is positive, the long one is positive, the short one is negative. So I'll just draw in my current's direction. Okay, so it'll be like that. Complete table 7.1 to show the reading on ammeters A2 and A3. Okay, how am I going to do that? The reading on ammeter A1 is 2 ampere. Okay, it's 2 ampere, yeah. And we take note, this is the current that flows through 2000 ohm. It is 2 milliampere. Okay, and in this the other path, right, because the main current comes out from here, so I call this I main, I3, because it's also going to be I3, right? The current that goes out from the battery is the one that comes back in, so it's I3. Then this is going to be I1 because of A1. This current that passes through this parallel path is going to be I2. So I have this idea of I3 equals to I2 plus I1, right? Because when they come to this part, since there are two paths, the current will split. But do they split equally? They will only split equally when the resistance in each path are the same. I say again, they will only split equally if resistance in each path is equal. But now they don't split equally, because one path is 4000 ohm, the other path is 2000 ohm. So you need to take note of this. other than I3 equals to I2 plus I1, which is the sum of the current in individual path is equals to the main path, which is I3 equals to I2 plus I1. Okay, you also need to have this knowledge that this is 2000 ohm with current of 2 milliampere. So this is the only information that I can work with. If I have I have R, I can actually calculate V. So V equals to IR. So the V is actually 2000 multiplied by 2 milliampere. And that will give me a value of 4 volts. That means from here to here, I'll have a potential difference of 4 volts. Which means this battery is actually 4 volts. Which then means the potential difference across here is actually 4 volts. Okay, it's 4 volts, yeah? So this is what I get from here. I have the I flowing through is 2 milliampere, that was given in the question, and the resistance is 2000 ohms, so I can straight away find the V. And because they are connected in parallel, same, in parallel, the voltage are the same. So 4 volts here, 4 volts here. Alright, so if now I have the voltage of this 4000 ohm, the potential difference across it is 4 volts, that means the current V equals to IR. The V is 4, the I is I2, what I call it just now. The resistance is 4000. I'm going to get I2 to be 1.0 milliampere. Therefore, A3 will be 2 plus 1, because sum in parallel, the sum of current is equal to the main branch current. Okay, so this one may be a little bit tough, but come on, you think about it. If the resistance here is 2000 ohm and I allow 2 milliampere and the resistance here is 4000 ohm, I will only get half of the current, right? Because there are small resistance, lesser current will flow through, right? By proportion. Then I can calculate it to be 1 milliampere. If not, then I find the voltage across here, which is V equals IR. Then I apply it to my parallel branches, and therefore I can then find my current in A2. So calculate the potential difference across the 4 battery. So actually I did that already, which is 4 volts, which means you are supposed to realize that due to the difference in their resistance by a factor of 2, the current will also be a difference of factor by 2. Okay. Okay, calculate the energy transferred. So this is energy in 5 minutes. Take note, this is my T, but it's 5 minutes, so I need to 5 times 60. I need to change it to seconds, so it's 300 seconds. Why do I need to change it to seconds? Because if I'm calculating energy in joules, everything must be in SI unit. So when do I calculate energy without SI unit? Is when energy that I calculate is expressed in kWh and when you see $sign. Okay, but other than that, if I have energy and expressed in joules, then everything must be in SI unit. So these are some common mistakes that students make. They just take 5 minutes as 5 minutes, and they want it in the 2000 ohm resistor, not the whole circuit, only the 2000 ohm. So the current in the 2000 ohm is actually 2.0 milliampere. Okay, which I just convert it to SI unit is 0.002 ampere. Okay. Yep. So what formula do I use? Energy equals to power times time. But power in electrical sense is IV multiplied by T. So I have my current in the 2000 ohm resistor, 0.0020 multiplied by the potential difference across it is 4 multiplied by time of 300. I will get a value of 2.4 joules. Okay. Question 8, figure 8.1 shows how the resistance changes during the first 1 second after lamp is switched on. So we have a resistance versus time. Suggest why the resistance of the lamp changes, okay, during the first 1 second. Okay, the answer is when the bulb is switched on, the filament heats up rapidly. Okay, the increase in temperature brings about more vigorous vibrations of the molecules and makes it more difficult for electrons to pass through, right? Because initially, let's say this is the filament. So because it is a solid, so the particles are arranged in regular and fixed position. But when I first turn it on, the filament will heat up. So if it heats up, the particles in the filament will actually vibrate more vigorously. So imagine I have electrons that are supposed to pass through. It will make it more difficult for electrons to pass through. Therefore, it causes the resistance to increase. Alright. So a fuse is used in a circuit of this filament lamp. Explain why the fuse is more likely to melt when the lamp is first switched on than when it has been lit for 5 minutes. Okay, so why is it that the fuse is more likely to melt? Because by right, okay, if you look at figure 8.1, initially the resistance of the lamp is lower. This is the resistance time graph for the light bulb, for the lamp. So initially the resistance is lower, right? If I were to compare to this part whereby it stays stable, the resistance is the same after this certain time. Okay, so initially the lamp's resistance is lower, so V equals to IR. If my lamp resistance is lower, my V is the same, right? Because I'm supplying it from the same battery, my current is going to be higher. So as seen from figure 8.1, resistance of the lamp is lower when the lamp is first switched on. This means that the current is higher initially using V equals IR. So if the current in the circuit exceeds the fuse rating, that is how the fuse melt, right? So after the initial increase in resistance, if let's say the fuse doesn't melt, after the initial increase in resistance, the resistance become constant. This is the resistance of lamp, nothing to do with the resistance of the fuse. Okay, you will see from here. After that, if the fuse survive, the lamp's resistance becomes higher and the same, right? Constant. So again, V equals to IR. Now my resistance increases. So the amount of current that flows into the light bulb will be lesser. So if it's lesser, then it's less likely to blow the fuse. Okay. Okay, question 9. I see two metal cans filled with equal masses of the same liquid at temperature 75 degrees. So same temperature, same mass, same liquid. Then I see dull black and I see polished silver. So this must be radiation. Okay, the cans are identical except that can A has a polished silver surface, B has a dull black. So by the way, black is a good emitter and good absorber. Okay, now where they are placed in? They are placed on a bench and the temperature of the substance in each can is measured every minute. The variation with time of the temperature of the substance in can A, can A remember is silver. It is shown here. Describe how thermal energy is transferred from the liquid to the surroundings. So what are some ways that we can transfer heat or thermal energy? Okay, so thermal energy is transferred first from the liquid to the metal can by conduction, right? Because they are just saying that the can is filled with this hotter liquid. So this can will then be hotter by having thermal energy transferred from the liquid to the can by conduction. So you need to state conduction, okay, because the liquid is in contact with the metal can. So this causes the metal to heat up until it reaches thermal equilibrium. Thermal equilibrium is a state whereby can and liquid has the same temperature with no net transfer of thermal energy. No net transfer of thermal energy. Okay, So after the can becomes hot, becomes the same temperature as the liquid, what happens next? The thermal energy is then lost to the surrounding by radiation, okay, and also by convection. Why is there convection? Although there are lids, okay, there is convection within the air within the can, okay. And also, if let's say everything becomes hot, the surrounding is also air, so there will also be convection current. Remember, the air that is nearer this surface or this surface will be heated up, and therefore there will be convection current. Okay, so thermal energy is lost to the surrounding by radiation, and to a smaller extent convection, as the air around the metal can is heated up, becomes less dense and rises up, taking thermal energy away. So you need to talk about conduction, convection, and radiation. Okay, now on figure 9.2, sketch the variation with time of the temperature of the substance in can B for temperatures between 75 and 35 degrees. Okay, so now they want us to sketch for can B. Now can B is actually what do you call that, dull black. So it is going to, the temperature is going to drop more rapidly, okay, more rapidly. But why is it that at 55 there is no change in temperature? Because possible the liquid is freezing. That means it is changing state. At 55 degrees. Okay, changing state at 55 degrees. So, because black is a better emitter, okay, so it will drop. The change in temperature will take a shorter time because it's a black color. Black color is a better emitter, and the surrounding is actually cooler. Okay, the liquid is hotter, the surrounding is cooler. So thermal energy will be radiated, right? Will be radiated. Therefore, we will say that it is only a good emitter in this case. Okay, for the context, it will be a good emitter, and then it will reach the freezing point much earlier. And doesn't matter whether it is what you call that? Doesn't matter whether if it is black or polished silver. At 55 degrees, the liquid will actually freeze. Then once everything has frozen, then it will decrease in temperature again, because again now it is still hotter than the surrounding at 55 degrees, and by this point all the liquid in can B has already become solid, but it is still at a temperature of 55 degrees, so it will actually drop to 35 degrees at a higher rate. Okay. Okay, question 10 is a drawing vector diagram. It's no longer in the syllabus. Okay, then now we go to section B and we see that it is on electromagnetic waves. Okay, so for section B, they actually give us wavelengths. So these are all wavelengths, yeah, of EM waves given. Okay, so they are actually arranged in terms of their order in the EM spectrum. So radio wave has the highest wavelength, gamma has the lowest wavelength, which means radio is going to have the lowest frequency, right? And gamma is going to be highest frequency. Okay, so state the speed of ultraviolet waves in a vacuum. It is 3 times 10 to the power 8 meter per second. So this is important. You need to sort of memorize it. Therefore, they ask us to calculate the frequency of ultraviolet waves of wavelength 10 nanometer. Now nano is actually 10 to the power of minus 9. You need to know this. So if this is wavelength, it has 10 to the power of minus 9 meters. The speed is actually 3 times 10 to the power of 8. Then the formula that we use is V equals F lambda. So 3 times 10 to the power of 8 equals to frequency, which is unknown, 10 to the power of 9. Then we do our math. The frequency will then be 3.0 times 10 to the power of 16 hertz. Okay? And this whole thing is 4 marks. Okay, 4 marks. Now, state the order of magnitude of a diameter of a typical atom. So, name the region of the EM spectrum that has a wavelength of this same order of magnitude. Wow. So, even for me, I won't really memorize it. Okay. So, maybe just before your exam, for your O-level, you should memorize the size of the typical atom. Okay, it's about 10 to the power minus 10, so this corresponds to the X-ray region of the EM spectrum. For me, I wouldn't get these 2 marks because I wouldn't have memorized the size of a typical atom. Okay, but that was in 2014, alright? Now, microwave, radio waves, and infrared waves are used in telecommunications. State one use of each in telecommunications. For this one, I will know how to do. Okay. So the answer will be Okay, radio waves are used in land-based direct transmission of television and radio signal. Microwaves are used in satellite communications and even in handphone signals. Okay, infrared is used in remote controls and for long-distance communication in optical fibers. So you need to relate your answers to telecommunications. Okay, so you cannot just say, oh, microwave is used in microwave oven. You won't get that mark. So 1 mark for each correct application. Okay, then now we go to the last question. It is a simple form of an electromagnet. So we'll be, and we see that there's a battery. So whenever current flows, okay, you can actually mark out the direction of this current flow. Then you can use your right hand grip rule to know what is the direction of the poles of this electromagnet. So when the switch is closed, an iron ball is held on the iron core. Iron ball is actually a magnetic material. What are the other magnetic materials? It will be iron, cobalt, nickel, and steel. Okay, so explain why a current in the coil causes an attractive force between the iron core and the iron ball. So this is concepts linked to electromagnetic. It's linked to magnetic induction. Yeah. Okay, let's look at the answer. Okay, when the current is switched on, the iron core magnetizes due to the current in the coil to become an electromagnet, right? Whenever current flows, you'll produce magnetic field. So this iron core will actually then become an electromagnet with a north pole at the bottom of the diagram. So please check whether is it north pole. So if you use your right hand grip rule and you have traced out the direction of all these currents, you use your right hand grip rule, yes, your thumb will be pointing downwards. So this will be my north pole, and therefore this will be my south pole. Okay, so the north pole of the electromagnet induces, this is important, a south pole in the iron ball, and as unlike poles attract, you need to state the concept. The iron ball will then experience an attractive force because unlike poles attract. Okay, and why are there unlike poles? Because the north pole of the electromagnet induces a south pole. Okay, so you need to state the magnetic induction in the ball. Part B, the current is reversed in direction. State the effect, if any, on the magnetic field in the iron core. describe the effect on the force between the core and the ball. So what if now I reverse the current's direction? So I use red color. Okay, so I do this. Okay, then now you have to apply your right hand grip rule again. So why don't we use Fleming left hand? Because there's no external magnetic field, right? So if I were to use the red arrows and I apply my right hand grip rule, my north will be here, my south will be here. So what will happen to this side of the iron ball? It will then be induced with a north pole, right? So because it's by magnetic induction, but because opposites attract, right? Unlike poles attract, so the ball will still be attracted to it. Let's see how to present the answer. Okay, when the current is reversed in direction, okay, the magnetic field in the iron core is reversed. They want us to state the effect, if any, on the magnetic field in the iron core. So we need to say that the magnetic field in the iron core is reversed. So the south pole is now at the bottom, and the induced pole at top of the ball is now a north pole instead. Look at my red color drawing, right? The south pole is now at the bottom for the iron core, whereas the iron ball, the end that is nearer to the iron core, will now be induced with a north pole. Okay, will now be a north pole. So assuming that the current is the same, the force between the core and the ball remains the same, therefore there will still be attraction. Okay, it's still attractive force. So the switch in figure 12.1 is now open. The iron ball of mass 300 grams. So this is M, but it is 300 grams, so maybe I change it to 0.30 kg to be safer. It falls through a vertical height of 4 meters, so this is my H. Calculate the speed of the ball as it hits the ground. Okay, why are they calculating the speed? Because actually the ball initially was here. I draw a sketch here. H is 4 meters, and the mass is 0.30 kg, and they give us the G. That means I can actually calculate the amount of GPE at this position equals to mgh equals to 0.3 times 10 times 4. I will get 1.2 joules. Okay, 40. Sorry, it is not 1.2, it's 12 joules. Okay, so when this ball hits the ground, the energy will be transferred from the energy in the gravitational potential store to the energy in the kinetic store. So 12 joules will then be equals to half mv squared. So this is for calculating of KE. So 12 equals to half times 0.3 v squared. So my V, if I do my calculations correctly, I'll get 8.94. Okay. So state one energy conversion that occurs when the iron ball hits the ground. So now it's hitting the ground. It's not when it is falling. So it will be from kinetic energy, energy in the kinetic store, to energy in the internal store of the surrounding of the ball, which is thermal energy also. Okay, thermal energy. Okay, we have last question 13. A live wire of 240 volts mains is protected by a 15 ampere fuse. 3 kilowatts heater is connected to the supply. This is the 3 kilowatts heater. So name the wires P, Q, and R. Okay, and fully describe the function of the earth wire. So this is actually the fuse, and this is therefore the this is a switch. So P must be live wire, because the switch and fuse always connect to the live wire. Okay, then so we just trace if the switch is closed, current is going to flow this way, go to here, and then it will come out from Q, right? So Q will be neutral. Okay, because Q is like the return path. How about R? R is the earth wire. How do I know? Because this is the metal case. Whenever you see metal casing, there must be an earth wire. So R is connected directly to the metal casing. So R is the earth wire. So fully describe the function of the earth wire. This can be found in my notes. The earth wire is connected to the metal casing such that if there's an electrical fault and the live wire touches the metal casing, so you need to mention briefly what is the electrical fault, which is the live wire touching the metal case. So the current will pass through the earth wire, which has low resistance. So the current will increase and the fuse will melt, right? Because it is like a short circuit as it passes into the earth wire. So there will be more current flowing in the circuit. The fuse will then melt, creating an open circuit. So this prevents the user from getting an electric shock if he were to touch the casing. So besides just directing current into earth, you must also talk about the implication on the fuse, because there will now be more current flowing. So the fuse will melt and therefore it will create open circuit, right? Okay, so the user wishes to connect a 2 kilowatt heater in parallel. Discuss using suitable calculations whether this will be a sensible idea. So what is the calculation? What values are we given with? So this fuse is 15 ampere, the live wire is 240 volts. And if they are connected in parallel, if I were to draw something similar like that, this is the 2 kilowatt, this is the 3 kilowatt. They are connected in parallel, right? And over here I have a potential difference of 240 volts. So if both are switched on, that means this 2 kilowatt heater will have a 240 volts of potential difference across it, similar to here, 240 volts. So this is my V, this is my P. So I can actually calculate what is the current that passes through the 2 kilowatt heater using P equals to IV. Therefore, 2000 watts over 240, I will get a certain value of then I do it for the 3 kilowatt, and because it is connected in parallel, the power is 3000 over 240. Therefore, I'll have a value of 12.5 ampere. Now, this will be 8.33, this will be 12.5 ampere. This is 8.33. So the total current that comes out from the main supply will be a sum of total current will be 8.33 plus 12.5. So I have a total value of 20.8 ampere. But remember, my fuse rating is only 15 ampere. So it will exceed this fuse rating value, and therefore the fuse will blow every time I turn it on. So it is not a good idea. Okay, so please do not write things like, oh, the whole thing will explode or what. You can actually use the calculation to show. Okay, so this is the calculation. Okay, you can take a look. Now, the element in the heater is made out of metal. Using kinetic theory, describe the effect on the atoms of the metal as the temperature rises. So as temperature rises, the kinetic energy of the particles will increase, right? Will increase, therefore they will vibrate more vigorously about their fixed position. Okay, let's take a look at the answer. Okay, as temperature increases, the atoms gain internal kinetic energy and vibrate more vigorously about their fixed position. Spacing between the molecules will increase and the frequency of collision between the atoms will also increase. Okay, so I think that's the end of 2014.